Thank you guys for coming. My name is Waleed, and I'm going to talk a little bit about building a practical example using TensorFlow. And I picked traffic sign recognition because it's a little bit more interesting. You can use natural images rather than synthetic images or handwritten MNIST tests and so on. So I started studying deep learning about a year and a half ago, and kind of throughout the process, I kind of came across a lot of challenges, so I thought I can share some of the things I learned. One important thing I noticed is that most of the tutorials either give you something super simple, or they give you something too complicated, or they give you something deep in math. So that makes it harder to kind of starting out to catch up and learn about it. So I'm going to make my presentation a little bit more practical. I'm focusing on building a step-by-step process to get to a working model. What I'm going to build is not necessarily the process you would follow for something that you would use in production, but it's something that's much easier to explain. So this is part 2 of my presentation, but since not everyone has seen part 1, I'm going to start with part 1, like a refresher, try to go through it quickly, and then jump into part 2. All right. Okay. So I use Jupyter Notebook to run the code, and this is going to be running live. If we have any technical problems, I'll switch to a local version, but as long as it's working, I prefer to be able to run the code in front of you guys so you can see it and kind of get a sense of how this is working, and maybe even change it on the fly. So let's see. Classification. All right. So part 1. In part 1, I start with the very basics. So basically, what's the simplest possible model that you can build that gives you some results? I'm using TensorFlow. This notebook is also available online on GitHub. But I modified this a little bit to work with TensorFlow 1.1. The one I have online works on the previous version. So I will push this after the presentation. And I also have a Docker image if you don't want to install all the libraries that you need. So that's available as well. All right. So the first thing in any model is the training data. In regular programming, you write the rules yourself, but in deep learning, you're kind of training the model, you're programming the model using the training data. So whatever you give it, it will learn that. So picking the training data, manipulating the training data becomes an art form that you use to indirectly train your model. So for this process, I just went online, Googled for traffic sign training data set, and I found many. I picked the Belgium traffic sign data set. It's a fairly small data set, 170 megabytes for training, and a separate 76 megabyte for testing. So here we go. I'm not gonna go through every line of code. But once we get to the interesting part, I will zoom in a little bit more. So the first part here is loading the data. The data comes in a file. You uncompress it. You get a list of directories. Each data set comes in a different format. So unfortunately, it's a little bit of a pain to kind of spend some time to understand how it's formatted, write the code to load it. And let's see. I'm going to restart this. So this is kind of starting everything from scratch, and I'm going to clear all the outputs. So this way, we're running live. So the first thing I'm going to run is the imports. And then loads the data and keeps it in memory. This data set is small, so it's OK to just load the whole thing, keep it in one big matrix, no problem. So for simplicity, that's what I'm doing here. We have two variables, images and labels. One contains matrices of the images. The other contains the numerical values of the labels. So when we say labels in deep learning, usually we're referring to a number that we could map to a string separately, but the model only deals with the numbers. So next, we want to see what this data set looks like. So let's do that. So we have 62 labels. So this data set contains 62 different traffic signs and a total of 4,575 images. So it's a fairly small data set. All right, so let's display it and see what the data looks like. This function, display images and labels, simply displays them. Displays an example from each label. So this is going to take a little bit. There we go. OK, so label 0 has 15 images. Label 1 has 110. Label 2 has 13, and so on. And this gives you a sense of what the data looks like. So if you're starting with deep learning, invest the time to actually look at the data. It's useful exercise. Write code to examine it. Write code to do statistics on it. Write code to visualize it, because this is your tool to train the model. And a lot of the bugs you might encounter later could be because the data has a problem. All right, so so far it's easy. We haven't even started in deep learning yet. We're just looking at images. Here I want to look at one label and see all the images from it. So unlike the first one, where I'm just looking at all the labels, here I want to take one and display that. So this is label 32, and these are the images in label 32. So here we already kind of catch a problem. Label 32 is a speed limit sign, but they treat each number, the numbers as irrelevant. So they have one label for different speed limits. So this is important to know, because later on, if you're expecting 70 to be a speed limit sign and 50, maybe you're thinking it's a different label, and you think there's an error, but there isn't, or you think your model is not learning the number inside the images, it's because every time it gets a different number and it cannot figure out what the shape of the thing looks like. So it's important to understand how the data is organized. So here we go. Now, another thing you might notice here, the images are not the same size. They kind of roughly square, but they're not exactly square. Some of them are a little bit taller, some of them are a little bit wider. And usually with neural networks, we like to work with matrices, and these are usually better as fixed. If you know the width and height, that makes things a lot easier. So the first thing I want to do is resize all the images to one size. There are many ways to do that. You can crop, you can stretch, you can whatever. And for here, I've just simply resized it to 32 by 32 to keep them simple, small. And that will cause a few distortions, but I'm OK with that. Let's see. So here I'm printing the sizes of images. So you can see some of them are 103 by 73 by 3, which is the RGB channels. The other is 271 by 179, kind of roughly around 128 by 128. And I chose to resize them to 32 by 32. Here, it's a simple loop through all the images, resize them, and display it again. Now, why exactly 32 by 32? I could choose a bigger image, and that might give me better accuracy or worse, depending on my model. I could choose smaller. I picked 32 by 32 by experiments. I tried 16 by 16. They were too small that I, as a person, cannot recognize all of them. So I figured, OK, most likely a model probably will have a hard time. 32 by 32 looked good. They are a little bit pixelated, but you can see, you can still tell what the sign is. So if I can tell, then there's a good chance that we can train our model to tell as well. So 32 by 32 it is. That makes the data smaller, and that makes the model much easier to train and faster. All right, so let's see here. To verify what I've done, I print the sizes. One of the interesting things about working with deep learning is that bugs are really hard to find. You don't necessarily get an error that says, OK, something's broken. Instead, and you don't even get a model that completely doesn't work. No, you get a model that works. It just might not give you the right accuracy, and you have no idea why, and you don't have no idea if this is the best the model can do or not. So do whatever, as much as you can, to avoid and catch bugs early. And here, this one actually makes it easier for me to catch a bug, where I'm printing the dimensions of each value, each image. And I'm also printing the minimum and maximum values. So you see the minimum is close to 0. The maximum is 1. I did the same thing here. And here, the minimum is 0. Maximum is 255. So this is something that I caught during the development of this. It's like, oh, one of the functions that I did actually changed the range of colors from 0 to 255 integer into a float, which is 0 to 1. That turned out to be the resize function. So great to know that, because otherwise I would have divided by 255 later and end up with a much smaller amount, which is going to make it harder to learn. But I already want the values to be between 0 and 1, so perfect. I'm just going to keep it that way, and I don't need to divide by 255. All right. So far, we haven't even started with deep learning. This is just setting up the data and getting ready to train. Now, let's get to a smallest possible model we can write. OK. So I take my list of images and list of labels, convert them to arrays. And for verification, these are the shapes of my arrays. Labels are a one-dimensional array, 4,500 long. And my images are a four-dimensional array. The first dimension is the individual examples. And in each row, I have 3 dimensions, 32 by 32 by 3, which is the image. All right. All right, so this is the fun part. This is TensorFlow code. And in TensorFlow, the way it works, you use Python to build a computation graph. And then you tell TensorFlow to run that computation graph. In other words, the code you write is not what's doing the learning. It's the code that is building a graph which will you later run to do the learning. So the graph, they do it this way because once they have a computation graph, they don't run it in Python. They run it in low-level code. They run it on GPU if it's available. And for optimization, that's how we do it. That makes it harder to debug that code, by the way, because you can debug your Python code, but that only tells you if you're building the graph correctly or not. But if you have a bug inside your graph, or let's say you're dividing by 0 or whatever, you cannot put a breakpoint, you cannot debug it. So another reason why do as much as you can to avoid bugs early on, because bugs are very expensive in deep learning. They're more expensive than in coding because they take a long time to find. I guess you can see, you can feel my pain with that part. But all right, so the first thing we do, we create the graph. I'm going to make the font bigger. All right, so the first line, creating the graph object. Then On this graph, we create two placeholders. Placeholders are TensorFlow's method of saying, this is how I use the data from the outside world. The outside world being our Python code, and the inside world being the computation graph itself. So I create two placeholders. One has a shape of none, 32, 32 by 3. None means this dimension can be whatever value. It's not important. And this is my batch dimension, which is the examples. By setting it to none, I can run this model with 1 image or 10 images or 1,000 images, doesn't matter. If I set it to 7, for example, I can only run this model with 7 examples. The size of the image is fixed, 32, 32 by 3, and then the labels, it's a one-dimensional array of size none, which means whatever size. Then I take the images placeholder, pass it through a flatten function. So the images placeholder is, like I said, 32 by 32 by 3. So it's a 3-dimensional array for each individual example. I flatten it to a straight line. So now I have a 2-dimensional matrix. The examples are the rows, and each row contains all the pixels, which is going to be 32 multiplied by 32 multiplied by 3, which is 3,072. Is it clear so far? Can you do the same thing with Keras? And the answer is yes. Keras is an API on top of TensorFlow. It just simplifies things, but the concepts are the same. The question is why we don't have a shape associated with labels. So we do have a shape, which is it's one-dimensional. We just haven't determined the length of that dimension. And the length is the number of examples. It's the first dimension is always the examples. So if I set a shape, then every time I run this model, I have to always run it with that fixed number of examples. If I set a length. So the shape is one-dimensional. The length of that one dimension is not determined. Equally to the images placeholder, the first dimension is the number of examples, and that's none to make it flexible. The question is, what if your training set is really large? And so the main concepts work the same. And when we go to the second part, I'll kind of dive in more into that. But the concept is the same. It's just you end up with dealing with scale a little bit. So the question is, can you look at all these images? Obviously, you can't, and that's a problem. And then, but this is not a deep learning problem. This is a human outsourcing, organizing, finding creative ways to inspect the data and make sure it's good kind of problem. It's not related to the technical part of it. The question is, if it's the large data set, how can you find out if there are duplications? This is a typical data management problem. You can create a hash. You can outsource it on Amazon Mechanical Turk. It's whatever you want to do. It's a data management problem. All right. So we flatten the image. And then out of all this code, this line is where the work is being done. This line says, I'm going to create a fully connected layer that takes the images, the flattened images, and returns what we call logits. This kind of looks like the network we're going to build. The green on the left, this is the input. So this is going to be a lot of pixels, exactly 3,072 pixel values, like RGB values for each image. And then I'm creating a fully connected layer. What does that mean? The layer on the right, there's a neuron. Each circle is a neuron that takes input from all the pixels. So the left is the pixels, the right are the neurons. Each neuron, and remember, I have 62 traffic signs, which means I will use 62 neurons. So my network here, as simple as it can get, one neuron for each traffic sign. And each neuron is connected to every pixel in the input image. So imagine the first neuron is for traffic sign speed limit, the second one is for the stop sign, and so on. And the RGB values get inputted to each neuron, but get multiplied by those little W's. These are the weights. So I'm going to have, the number of weights I'm going to have is going to be 62 multiplied by 3072. That's the whole of the model. These are my weights. And these weights determine how the model works. If one of those W's is 0, means that neuron is not getting value. Whatever the pixel value is going to be multiplied by 0. It's not going to influence the value of that neuron, and so on. Go ahead. The left ones are pixels. They are RGB value of pixels. And the right ones are operations. They take the input from the left, gets multiplied by the W, gets added together, all of them, and that's how you end up with the value of the weight. Sorry, to repeat the question is like, what was the input and what was the output? All right. So the simplest possible network is this line of code that says the input is the flattened images, the output is 62, meaning I have 62 neurons, and then ReLU, that's an interesting one. In this particular example, this is not very useful or effective, but it's kind of a standard, so I just put it there for explanation. ReLU is a nonlinear function, and usually when you build deep learning models, you have a layer of multiplications, which is you multiply the input value by the weights, and then you have a nonlinear function. Sometimes it's the logistic function, sometimes it's tan. Recently, more commonly, the ReLU. The ReLU is simply a max. Takes the value, trims if it's below 0, it becomes 0. If it's above 0, it passes it exactly as it is. So if you want to draw it, it looks like this, the one on the left. And I'll get back to that. It's simple. Value before 0 gets trimmed, value above 0 gets passed the same way. And turns out this is what allows the model to kind of recognize more complex patterns that are not linear. Right. So we got the logits. So what does the logits mean? We're going to get 62 logits for each example. And each one is the output of a neuron. So those logits represent the prediction of the model. A high value tells me that this model is getting, has a good confidence that it is the one, that it recognized what it's looking for. If a neuron produces a negative value, then it means it's not finding what it's looking for. The values of logits are not unbounded. It could be from minus, a gazillion to plus a gazillion. All right. Usually, when we work with neural networks, often we want to convert the logits to probabilities. In this particular case, I don't really need to. I just need to pick the biggest one. So the logit that has the largest value, that tells me that is the prediction. So I do an argmax, and this argmax goes through every row, picks the largest one, and gives me the index to it. Go ahead. The question is, what if you don't know how many traffic signs you have in your data set? Your data set is labeled. That's why we call it a supervised learning. So you know exactly, these are the images, and someone has done the hard work of going through each one and putting a label on them. So you should know. All right. So predicted labels, that will give me an array of length equal to the length of my examples, and each value in that is the index to which logits got the highest value. All right? Next step, I need to tell the model how to recognize a good output from a bad output. So The good output is the label that I know. It's part of my training data. So it's going to be a list of numbers. And the output that comes from here, from the logits, is whatever the model is creating. So what I do, compare the two, and if they are the same, perfect, no learning needed. If they are different, then I go back and modify those weights. That's the back propagation process. I go back and modify the values of the weights to make the model produce the value that I want. So this is the loss function. The kind of loss function you use depends on the model itself. For a classification problem, cross entropy is the most popular and the most common approach. And what cross entropy means, you compare two lists of numbers, and if the inputs are zeros and ones, the labels, the ground truth data is zeros and ones. 0 is for labels that are not active right now, 1s for labels that are active right now. And the output from the model is going to be numbers between 0 and 1, hopefully, if you do or since in our case, could be between minus infinity to plus infinity. So cross entropy compares these two vectors, and it will have a high loss value if they are different. It will have a low loss value if they are the same. So my goal is to make the loss as small as possible. The next and almost the last one is the optimization method. TensorFlow kind of makes that easy for us. The Adam optimizer is pretty good for most applications. So I use the Adam optimizer. I give it the loss operation, and I say minimize this. In other words, every time I run this operation, it will look at the predictions from the model, it will look at the data and say, okay, what's the difference? And go back and modify the weight to reduce that difference. So this is my training operation. This is my training line. Go ahead. The question is the optimizer like a gradient descent? Exactly. So Adam optimizer is an improved version of gradient descent that has a little bit more intelligence inside of it that kind of try to recognize which weights are changing fast, which weights are changing slower, and kind of tries to optimize it better. So it works faster than a gradient descent. And then the last operation I'm creating is global variables initializer, which simply just goes in my computation graph. It goes through all the variables and set them to 0 or whatever the initial value is. So this is my model. And like I said, the Python code does not run the model, does not run itself, do the training. It just creates a computation graph that I need to run later. So let's run this, and it should print a few values. So I'm printing images, flat, logits, loss. I'm printing some of those variables that I created. And you can see those variables are not actual matrices. The images, placeholder, and the images flat. It's a class. It's an object of type tensor that has a name, and it has a shape, and it has a type. All right. When I want to run my model, I run it in a session. So I'm not going to dive deep into that. You create a session, you call run, and you give it the operation you want to run. The first one you always run is the initializer operation, which we created above. It just sets everything to 0. And then this is the training loop. So I'm training for a range from 0 to 201. The reason 201 is for every 10, you can see the last line, I print. So I want to make sure that I print the last value. And the real line that does the work is this one. All I'm doing is I'm saying session.run and the train. The train, if you remember, it's this variable here that I created, the Adam optimizer. So I'm just saying run this, and that's all I need. But I'm also going to say run the loss as well, so I can get the value and print it. So Okay, drum roll, let's run it. So this is the model learning. And you can see the value of the loss going down. Okay, done. So let's test it. So here I'm going to pick 10 random images, and then I'm going to do the session run again, but I'm going to say run it on the predicted labels. And it gives me these values. These are the predicted labels. It's hard to know whether they're right or wrong, but I can display them next to their corresponding images, and that makes it more interesting. There we go. Okay, so we got several correct predictions and a few wrong predictions. So we're already making progress with a very simple model that has just one neuron per label. And I mean, pretty good for like a few minutes of training. Go ahead. The question is, do the image quality of the training data influence the results? And the answer is definitely, for sure. And this is one of the things you do. Like if I'm doing this for a production, I will probably try it with 32 by 32. I will try it by 64 by 64. I will do a lot of experiments to see which one gives me the best results. All right. Now, it's hard to tell how accurate the model is. This is subjective. It looks like it's just doing something right, but how good is it? So I'm just going to do the same thing, but this time I'm just going to run it across a lot of images and just add up the correct and the wrong predictions and print the results. And also I'm going to do that not on the images that I use for training, because that would be cheating. These images that the model already saw, the model could have memorized them. So that's why I have a training data and a test data, or the validation data. So I run this on another set of data. So here I'm loading the second set. I have to resize it to 32 by 32 again, because my model expects that size. And then finally, I'm going to run the predicted labels operation on them, but I'm going to pass the whole validation data set to it. So here I'm loading the validation data set, just visualizing to see how it looks. And I'm printing the accuracy here. And the accuracy is 62. So 62 of our predictions are correct. That's the accuracy. That's the more scientific calculation of assessment of the accuracy of this model. So when I got this, I was like pretty kind of surprised. I mean, I thought such a simple model will not get to that level, but it's working pretty nicely. And most likely, it's finding certain patterns, like blue maybe and more likely this, kind of red, more likely that. And it's not fully understanding what's going on, but it have found some statistical patterns and uses those to do its prediction, and it's generating pretty good results. So that's part one, where we built the simplest possible model that give you results. So I'll take a few questions about part one. So the question is, do each neuron start with different values? And the answer is yes. By default, when you create weight variables in TensorFlow or most other libraries, they initialize them to random values, random. The reason you want them random is you don't want them to start with 0, because that might cause problems where they start to sync together. Like you get an operation that says the weights need to go up, and they all go up the same value, and you end up with some kind of like they don't learn as they should. So you start them with random, and then they kind of arrange themselves in the process. Yes. The question was, can you visualize the weights? What's going on? And the answer is yes, soon. The question is, why would a neural network work better than SVM? The answer is, sometimes it works better, sometimes it doesn't. Depends on the data, depends on the situation. With a neural network, usually you can make it deeper. And recent results show that deep networks are performing better. But there was a time when SVM was performing better, so who knows? Yeah, maybe SVM makes a comeback, we don't know. The last operation is session.close, and that basically destroys the session. And I'm not going to do that here because I don't need to. All right, second part. So the same thing here. I'm going to restart everything and clear the output. So we want to run fresh. Okay. All right. So we proved the concept. We figured out that a simple model can work. Now, how can we make it better? So we start with the normal imports here. And here, just for the sake of clarity, I repeat model 1 here. So I'm not going to go through that. I just took the whole code from the first notebook, compacted it in a small set. So I have a class called model 1. And it has the same exact things that you saw. I'm going to go through them very quickly. 2 placeholders for the images and labels. We flatten the images. We pass them to a fully connected layer. We get the logits. We do an argmax to find the largest logit in each example, and that's our prediction. We have the loss function, the training operation, and the initialization that resets all the variables to their initial values. And then creating a session and running it. So let's create this. The functions for loading the data, I also compacted this a little bit. Now the function loads the data and resizes it at the same time. So I'm loading the same data set. And the same functions for visualizing the data. So this is intended so that if you're starting just with Notebook 2, you can jump to this right away. So we've seen all that already, so I'm not going to go through that again. Okay, the training. Again, I cleaned up the code a little bit. Now we have a train function that has the loop inside of it, and an evaluate function that calculates the accuracy. And this allows me to display the accuracy while I'm training. In the previous one, if you remember, I could only display the loss. So this is a little bit of an improvement here. And I create the class. I run it for 200 iterations. And it's training here. So you can see here, the number on the left is the number of iterations. The second number is the loss. The third number is the accuracy. And you can see the accuracy going up. And this time we got even better accuracy. We got 71%. And this is just because it's kind of random. I'm not optimizing this to like its best it could be. I just ran it for 200 iterations. If I run it again, I might get a different accuracy. But this is pretty cool. We already got 70% on this very simple model. So let's look inside of that. So the first thing I want to do, we said it's an execution graph, right? A computation graph that contains nodes. And some of those nodes are the weights. So I'm going to say for the M1 graph, print all the trainable variables. And the trainable variables are the weights. So what did I get? Fully connected / weights, fully connected / biases. So if you know any of the basics of deep learning, usually for each neuron, you have several weights that correspond to the number of inputs to that neuron, and also has one value, which is the bias, which is the kind of push the output up or down a little bit. So our weights is a matrix of 3072 by 62. 3072 is the number of pixels multiplied by 3, which is RGB, and 62 is the output. And then the biases are 62, which is the number of neurons. So visualizing weights is tricky because weights, they're not naturally visual. I mean, they don't have an inherent visual representation. But this model, because it's so simple, it could, because all the weights are connected to pixels directly. So there is a pixel, there is a neuron, the connection between them is the weight, and it tells me if it's a high value, that means this pixel is important to the result. If it's a low value, it's 0, that means this pixel is not important. If it's a negative value, it means this pixel it has a negative correlation. It should, like, if it's red, if the pixel is the red part of the pixel and it has a negative value, it means the model doesn't want to see a red here. So what I do, I take this weight, 3072 by 62, just kind of reshape it a little bit to look like images, and then I display them as if they were images. So here I'm printing the minimum and maximum values for each matrix, just to kind of sanity check. And it looks like the values are between -1 to +1, sorry, 0.1, -0.1 to plus 0.1. Seems reasonable. And obviously, I need to kind of normalize them a little bit to display them as an image. This function, display weights, does that normalization for me. And let's see what's going on here. So here I'm showing an image on the left and the corresponding weights on the right. So if you kind of keep looking at it, you might notice some patterns. For example, label 7, the weights kind of look like the image. Same with label 8, label 13. But the others just kind of look like rubbish. So this tells me something is wrong. So first, the weights that look like the image, this is perfect. That tells me this model is looking for red in this area, looking for black or white in certain areas, and that explains why it's able to recognize that image and give you a good prediction. But the ones that are kind of random, that means the model hasn't learned much there. And if you stare at it for a while, you might find another pattern, that the labels that have a lot of examples, they have weights that look nice. The labels that have few examples are random. So you see, like, label 0 has 15 examples, and it's kind of random. Label 7 has 157 examples, and the weights look nice. So that kind of gives me a hint towards where my problem is. The model is learning for weights from labels that have a lot of examples, but not learning from examples, for labels that don't have a lot of examples. So this took me a little bit of research to find out what's going on. So the result is two issues. One, I'm taking the whole data set and feeding it, all of it together, to the training operation. In other words, when the model looks at all these examples, calculates all the predictions, subtracts the ground truth, calculates all the losses, which losses will dominate? It's the ones that have, of the examples that have exist a lot in the data. Go ahead. So the question is, or the remark is, the network seems to be trying to replicate the image, and why don't we just replicate it and get it over with? I mean, obviously you could, and you'll probably get some results, but this is only happening because we're using one layer. Once we go beyond one layer, it gets more complicated. So since we have just one neuron per label, that's the best thing it could do. All right, so the first thing, because I'm feeding the whole data at the same time, which makes the code simpler, but obviously it's not a good idea here. The second issue was, remember that ReLU function that I mentioned earlier? It turns out it has a well-known problem. They call it the dying ReLU problem. What that means, so let me go back to that image. So the ReLU function is on the left. If for whatever reason your random initialization of your weights caused the output of that ReLU function to always be negative, then it will, and the gradient descent works by calculating the gradient, and the gradient is 0 in the left side, means if your output is in the left side, it's going to get stuck in the left side. If your output in the right side, it can look at the gradient and know whether to go up or down. So that's one of the reasons that ReLU could die. And this problem happens more in smaller models. If you have a bigger model, multiple layers, and you're kind of careful with your initialization, you can avoid it. But in this case, because it's a simple model, it actually was a fairly big problem. So to fix these two problems, we go to model number 2. Oh, let's see. Just for kicks, I'm going to print the histograms of the weights as well. So the weights are just matrices. So I'm just going to say, I'm going to print the histograms and see what they look like. And you'll see a pattern. The weights that look good, in here, they also look like a normal distribution. The others look kind of white noise. The question is, are these histograms probabilities of being an image? The answer is no. These are, you have a weights matrix, and this kind of displays how many of those weights are valued at 0, how many are valued at 0.1. It just gives me how my weights are distributed, the distribution of my weights. And yeah, this normal curve, like for example here, label 24, I want to see that, because that tells me that most of the weights are close to 0, which means most of the pixels don't contribute much, but there are a few that contribute positively and negatively. So this is a good shape for a weights histogram. All right, so model 2. This one, I fixed these two problems. I replaced the ReLU function with a leaky ReLU function, and this is the definition here. As you can see, it's a very simple function. Instead of cropping the value below 0, I give it a little bit of a gradient. So it's not exactly horizontal, but it's also not linear. So I still have a nonlinear function, but I can calculate the gradient on the left side as well. All right. So the code is simple. Just if it's greater than 0, you pass the same value. Otherwise, you pass the 0.01 in this case, kind of like a much smaller version of that, of the x. And another change I did in the model is passing another variable in the model called global step. It's a convenience variable that TensorFlow updates for you that counts the number of steps. So this way, instead of having my own variable to count how many steps, this counter is inside the model. And you'll see why it's useful a little bit later. And in where is that line? This line, the most important part, instead of ReLU, I replaced it with leaky ReLU. So let's run this, and I also created a function called train minibatch. So this, instead of taking the whole data set and feeding it and calculating the weight, it takes them in batches. So it picks random, see here, it just picks random examples from the set, 50 at a time in this case, and feeds them to the model, then calculates the gradient descent and does that again and again until we're done. And oh, look at that, already done. So, and we have an accuracy of exactly 90%. So this is called stochastic gradient descent. as opposed to the typical gradient descent where you feed the whole data. This, you feed it parts. And it's actually performs better because it allows, in each batch of 50, every example has more say and kind of pushes the weights in its direction. And the randomness of it allows more variety, which allows the weights to go can explore more areas in the space, in the multidimensional space. So this model got us 90%. Let's do the same thing. Let's visualize the weights. That's much better, right? So even the labels that have a few examples got a fairly nice looking weights. And that explains why we got a better accuracy. So there you have it, 90% accuracy with a model that has one layer. And we would have not known about this problem if we did not look at the weights, which, to emphasize my previous point, it's really hard to discover bugs in your deep learning model because there's no flag that tells you, here, there's a bug. It's just like the accuracy is like, we thought 70% was pretty good for a simple model. Turns out you can do better. All right, and then we also display the histograms, and those look much better. Okay, so far we're still on a very, very simple model of one layer. What if we add more layers? And this is not as complex as it might seem. It's like you take the same code, and then you just repeat this line. Instead of taking the images, passing it through fully connected layer, and getting the logits, I take the images, store them as H1, then input H1, like hidden layer 1. Use H1, pass it through another layer, get H2, then pass H2, get logits. And that's pretty much the only change I made. And now suddenly I have a deep learning model. So let's see how this performs. This is going to be a little bit slower to train. I'm running this on EC2 on a P2 instance. So the training is pretty fast. But even if you run it on a CPU, this will be pretty fast because the model is very small and the images are very small. Okay. It has a randomness to it. Okay. So as we get closer to 100, obviously it gets harder to climb. So here we got 92%. And that's because we have several layers, and that allows the model to recognize more complex patterns. And all right. Now visualizing the weights becomes much harder. So I'm printing like I did before, I'm printing the trainable weights. And here,
how do you choose the layer sizes?
in this case, I just picked numbers. So the question is, how do you choose the hidden layer sizes? In this case, I just picked numbers that kind of felt right. But typically, you would do experiments. You will also, your understanding, it comes with experience, understanding the complexity of your data, and you run experiments. So my weights here are more complicated. The first one is still 3072 by 200, and by 200, not by 60, because now the output goes to a hidden layer, which I picked as 200. Then the hidden layer takes 200, generates 100, and then the 100 gets input to another layer that generates 62. So now my weights don't look like images anymore, so I cannot just reshape them into images and display them. But I can still print them, display the minimum and maximum value. I can try to display the weights of the first layer because those are connected to pixels, so they kind of tell me what pixels the model is kind of caring about. But now this only represents the first layer. So you can see the images look a little bit messier than the first one, because now the knowledge is represented in multiple layers. And unfortunately, I cannot visualize the other layers other than using histograms. And it looks like they look OK, but it's pretty hard to like really visualize it. All right, so the next step is convolutional networks. Convolutional networks are very effective in image recognition and classification. The main concept is, so we built this simple fully connected layer that looks at 32 by 32. Imagine you have a smaller network, a fully connected network that looks at a small patch of 3 by 3. So that's what a convolution is. It's a small fully connected network that looks at a patch of, let's say, 3 by 3 or 5 by 5, and then it kind of goes, scans the image and keeps doing the same thing for each patch. And instead of our network looking at the image and the output being labels, the smaller patch, it's doing the same thing. It's looking at a patch and trying to predict what's in that patch. And what's going to be in that patch is, it's a solid patch, it's a bright patch, it's a dark patch, it's a edge patch, and so on. So it will try to predict those kind of little patterns in each patch. The next layer will take those and do the same thing on them, and will take those edges and kind of empty areas and lines and connect them together and recognize maybe squares and corners. And then the next one will use those to connect, to create more, to understand more complex patterns. The code, it starts to get a little bit more advanced, more complicated here. So let's see, we're almost running out of time. So I'm going to run it and then explain the process while it's training. OK. So just to explain the graph. Now this model is training. The top graph is the accuracy. The bottom one is the loss. And you can see with every iteration, the number of steps at the top, the training accuracy is going up. The validation accuracy is also going up, but it's not catching up. So with every iteration, I'm training and then running the prediction against the validation set, which I have. The model does not get to see it, to train on it, and then print that. And so that's my model training. And you can see it's, because it's still a simple model, and I have a GPU on this instance, it's training pretty fast. And let's see, we got 93 so far. I might get slightly more. Let's see. So here I kind of went a little bit fancier and added the graphs and so on rather than just printing them, because we're starting to get a little bit more data. And in terms of the model, all of this code is just the training. But the key part of the model is this. So we got our images and labels, as usual. Then we pass through a convolutional layer, then a max pooling layer. Max pooling is when you look at a patch, and you get patterns from it. You look at another patch, another patch, another patch. Now you got 4 patches. You might want to say, OK, what if I take the most prominent features out of those 4 patches and pass them to the next layer? Because at the end, the top layer that will do the classification, it doesn't need to understand every little detail. It cares about the important ones. So out of every few patches, you do the max pooling, which is basically pick the top patterns that were recognized and pass them to the next layer. And then we do the same thing, another convolutional layer, and then another max pooling layer, convolution, max pooling. And at the very end, we do the same thing, the fully connected layer. So our first model was just this, the fully connected layer. It takes pixels. Now, instead, it takes features that got produced by the previous convolutional layers. And the rest is the same. You get the argmax, loss function, and so on. So not very different, but the results start to get better. Now we hit 94%. And interestingly, on the training data, we hit 100%. In other words, this model is able, if you show it any of the training images, with 100% accuracy, it can know all of them, which means it's cheating a little bit. It memorized many of them. But when you show it the validation data, it gets 94%, which is still good. So that's the convolutional model. Now, if you want to get better, you can add more layers. You can add more training data. You can augment your training data. For example, most of the signs, if you flip them horizontally, they don't change. So what if you flip all of them and you double your data? Or do a little bit of rotations. Add a little bit of random noise. Just give it more examples. This allows the model to recognize that noise, rotation are not important because I have seen multiple versions of these images and they all produce the same result. So yeah, there you have it. This is a convolutional network that we trained. We got 94 accuracy. And we can probably get better if we do more, but in the interest of time, I want to allow some time for questions. The question is, will those random modifications to the data get you to 100%, and whether you would use that to drive a car, to actually let the car drive. So the data augmentation, it does not insert new data. But the way it helps the model is, let's say, for example, for whatever reason, the guy who went out to take pictures of stop signs had a dead pixel in his camera, and you end up with all the examples of a stop sign having that dead pixel. Guess what? The model will look at that dead pixel like, aha, this one tells me that this is a stop sign. By adding this randomness, you prevent the model from picking on irrelevant data. So that's where it helps. And this is simple. This is like, is that close to driving a car? Not even close. Here the images are cropped where you get exactly just the traffic sign. The harder problem, hopefully if I get a chance, I'll do part 3, where you have a picture of a street and try to find the traffic sign in that larger image. That's a much harder problem. But this is kind of just an entry for something like someone who's just starting in the process. So the question is, you created 4 models. Is there a reason why one works better than the other? The reason is the first one was very simple, 1 layer. The second one, we fixed a few bugs in the first one. The third one, we added more layers. The fourth one, we went to a convolutional model and we added even more layers, so it became like 6 or 7 layers. So these tricks that you use, they're well known, and you can use as many of them as you can as applicable to your model, and you will get better results. The question is, can you visualize what the convolutional layers learned? And the answer is yes. I don't have it here, but I will probably try to do that and add it when I push this to GitHub. I'll be useful. Yeah. The question is, do the convolutions, when they slide over the image, do they overlap or not? It's up to you how you set it up. In this case, they do overlap. So that 3x3 patch or 5x5 patch moves 1 pixel at a time. The question is, can you use an ensemble of networks and average their weights and get better results? Often you can, yes. It makes things slower and more complicated. So when you're competing in a competition and that you want to squeeze that last possible 0.001 of accuracy, then sure, but otherwise it's not very practical in real applications. The question is, does TensorFlow run on GPUs? Yes, TensorFlow runs on GPUs and allows you to distribute the load on multiple GPUs. It also has support for multiple machines. This is training fast. We can see it training because I'm running it on a GPU. All right, well, thank you, everyone. Appreciate the time.